Hi everybody, Jonathan here. In this video, I will be giving you my take on section 2.3, which is all about calculating limits using the limit laws. So the limit laws are basically a large collection of properties of limits. For example, the first one says if you have the limit of a sum of functions, then that's going to equal the sum of the limits of each function taken separately. And there's a similar limit law for differences of functions, for products of functions, and for quotients of functions. Moving down the list, the limit laws also say things like if you have a limit of a function raised to a power, that's going to be the same thing as the limit of the function, where the whole limit is now raised to a power. And they also say things like the limit of a constant is a constant, the limit as x goes to a of x is just going to be a. And the last limit law says that the limit of a root of a function is going to be the same thing as taking the limit of the function and then taking the root of the resulting limit. Now, what's the point of all these limit laws? The point is that most limits are going to turn out to be kind of pointless. Because by the direct substitution property, it says if f is a polynomial or rational function and a is in the domain of f, then the limit as x goes to a of f of x is just f of a. In other words, you literally just plug in the value you're taking the limit at into the function. So why on earth did people go ahead and invent this whole new concept of limit if it's literally the same as just plugging into a function? Well, the reason limits exist is that it's only interesting limits where you can't just do this. Most limits, in a sense, are rather boring and you just plug in and are therefore pointless. But not all limits are pointless. Some limits are a lot more exciting and are going to take more work to calculate. So a limit is only going to be interesting when something goes wrong. What can go wrong? The most common thing to go wrong is you get 0 in the bottom of a fraction. Another possibility is that you have a piecewise defined function and that you're finding the limit at the point where the rule changes. Like when x is less than a, there's one rule, and when x is greater than a is another rule. And usually those just boil down to calculating a couple of one-sided limits and seeing what happens. We are primarily going to be interested in solving limits where you get 0 in the bottom when you just try to plug in. These types of limits are going to come in just a few types of categories. For example, one class is where you're going to have to expand parentheses. For example, the limit as h goes to 0 of 2 plus h, the quantity of 2 plus h squared minus 4 over h. Another type of limit is where you're going to have to factor. In order to solve the limit as x goes to 7 of x minus 7 divided by x squared minus 49, you're going to have to factor the bottom and hopefully get an x minus 7 to cancel out so you no longer get 0 in the bottom when you plug in. Another type of limit is when you're going to have to rationalize either the numerator or the denominator. If you try and plug in 9 here, you're going to get the square root of 9 minus 3, which is 0, divided by 9 minus 9, which is 0. And by rationalizing the numerator, you'll be able to eventually algebraically manipulate things so you no longer get 0 and then you can plug in. And the last broad class is when you have to just manipulate fractions, combine fractions, simplify fractions, things like that, in order to eventually algebraically simplify / manipulate the expression so that you no longer get 0 when you plug in. In this section, the book gives nice examples of the first 3 classes of these types of problems, but it doesn't have any examples of the 4th one. So I'll just go ahead and show you how to solve such a problem. So for example, suppose we want to find the limit as h goes to 0 of 1 over 4 plus h minus 1 over 4 all divided by h. So what you have to do is combine these fractions, and the only way to combine fractions is to make sure they have the same denominator. So here, if you want to have the same denominator, I can take this fraction on the left and multiply by 4 over 4, and I can take this fraction on the right and multiply it by 4 plus h over 4 plus h. And now, by the rules of fractions, this is equal to the limit as h goes to 0 of 4 over 4 times the quantity of 4 plus h minus 4 plus h over the quantity of 4 plus h times 4. Notice now that the denominators are in fact now the same, which means you can just add or subtract the numerators. which gives the limit as h goes to 0 of 4 minus the quantity of 4 plus h over 4 times the quantity of 4 plus h. You can distribute these parentheses and the 4's will cancel, and we wind up with the limit as h goes to 0 of minus h over 4 times the quantity of 4 plus h all over h. And while I could have done this earlier, I saved it till now. Dividing by a number, like we're dividing everything by h here, is the same as multiplying by 1 over that number. So this expression here is equal to the limit as h goes to 0 of minus h over 4 times the quantity of 4 plus h times 1 over h. At this point, you can go ahead and cancel those h's, which is what we want all along, because up until now, every time you applied to plug in h equals 0, you got 0 in the bottom. And that gives the limit as h goes to 0 of minus 1 over 4 times 4 plus h. Now plugging in 0 for h doesn't give you 0 in the bottom of a fraction, so we go ahead and plug in 0 and we get our final answer as minus 1 over 16.